There are few formal approaches to creativity. Of the one proposed so far by researchers on computational creativity, most emphasize search as a central mechanism to simulate creativity. Most often, generative art or computational creativity projects start by identifying a search space or conceptual space that corresponds to all the possible artifacts, behaviors, or candidates that would be the product of a creative task. For example, we can consider all the 8-measure-long polyphonic compositions, or the space of all the vectorial drawings on a 400 by 400 pixel canvas, or all the possible paragraphs of text that form a joke, etc. For each creative task we can consider, we can define a search space. The search space, sometimes called conceptual space or state space, can be represented and structured in many ways depending on the representation we choose. It can be as simple as a few parameters, or be a list, a graph, a tree, all the possible weights on an artificial neural networks, the transition table of a variable Markov model, or a parametrization of many of the formalism and algorithm that we looked at earlier in this class. In the spirit of exploratory creativity, the search consists of the generation of artifacts that are points in the search space, that are then evaluated. This is the classic generate and test process, and it can be sophisticated at will, but let's start with the simpler approaches. The most direct way to traverse the search space is by enumeration. By enumeration, we mean that every element of the search space will be produced or visited consecutively. The paintings of Piero Manzoni, like this ABCDEFG series from 1958, are a good example of early use of enumeration in visual art. Computer technology, through the notion of repetition and iterations, allows for more ambitious enumerations. John Simon's Every Icon is a 1996 generative artwork which slowly displays every 32 by 32 pixel bitmap possible on a finite grid. Leon Desage extended the concept to color images with the 2000-piece Image N, but it seems the search has altered as it is not online anymore. With enumeration, like with chance operations, the artist surrenders to accidental creativity. Enumeration is more systematic, ordered, and rigorous than chance, but also seems more desperate, predictable, and uncreative in some ways. Internet Directory by Daniel Temkin is a 2014 Twitter bot that tweets out every existing .com domain in alphabetical order. At the pace it is going, it will still be in the name starting with a number by the time we're all dead. Possibly the most interesting thing about enumerations is that they remind us how vast most search spaces are and how rare aesthetically pleasing or interesting parts are. The structure of the search space depends on the way artifacts are represented, but often enumeration unveils some local coherence in the organization of the search space. Most often, interesting parts of the search space are grouped together. If an artifact is of low quality, then the few surrounding ones are unlikely to be much better. A classic way to jump from one part of the search space to another is to consider the search space as a parametric space. We can then use randomness to visit random points in the search space. Reverse OCR is another Twitter bot by Darius Kazemi from 2014. It randomly selects a word and draws randomized vector lines until an OCR, optical character recognition software, recognizes the word selected in the first place. Once the word is matched, the drawing of the word gets posted on Twitter. Here are some examples of these drawings. The idea of search is not restricted to enumeration nor random exploration. There are many more economical or principled ways to search for new and valuable artifacts. One can try to define or explore the search space in such a way that traversing it produces only desired outcomes. If the search space is constrained enough, then we can proceed with uninformed search. In this case, we traverse the search space fully. Such methods can be categorized into forward search methods and backward search methods. In forward search methods, we start from the initial state and go to the final state, so that we're going from initial nodes to final nodes, from the root to the leaf, from the initial symbol to the terminal symbol, from facts to conclusions. We produce results by going from the axioms to the consequences. For example, we saw that A4-1 is a rule-based system that explores the space of all the possible paintings by starting from an empty canvas, with some paint of various colors and certain operations it can perform that structure its search space. A4-1 stops only when it considers the painting finished, that is, when its stopping criteria are met. But each traversal of the search space, each generation, is supposed to be an interesting artifact. Then you have backward search methods, sometimes called backward chaining, in which we go the other way around. We reverse engineer the solution from the goal to the initial facts, from the end state to the various components that are used to get there. For example, explanation systems are going backward from the state we are in and tracing back how we got there. Another example is a medical diagnosis system that can tell you what symptoms to look for to determine whether a given disease is present or not. It goes from the disease to the symptoms. Yet another example of backward search is the inductive methods to learn grammars by determining which rules would explain the generation of a variety of sentences in a given language or a variety of melodies in a given musical style. As part of its many modules, the Painting Fool by Simon Colton has an explanation module that is part of its architecture and that gives reasons why the agents made such and such choices when painting a piece. Irrespective of the direction of the search, the state space can be traversed in many different orders. Two classic strategies of exhaustive search are depth-first search and breadth-first search. With depth-first search, the choices, nodes, or individuals represented are explored or generated in sequence, and backtracking occurs from the first complete individual back to the root. With breadth-first search, all the options at a given level, that is, all the paths within a certain distance of the origin, are explored before the nodes and decision of the next level get reached. The idea of exhaustive search gives us the illusion of finitude. In 1893 already, in Lewis Carroll's Sylvie and Bruno Concluded, Arthur says, "The day must come, if the world lasts long enough, when every possible tune will have been composed and every possible pun perpetrated, and worse than that, every possible book written, for the number of words is finite." The truth is that the size of the search space for all permutation is usually so big that to see it as finite is just pointing at the discrepancy between ideality and reality. In most cases, the search space is too large to use an uninformed technique, and informed or heuristic search must be applied. Heuristic strategies are very widely used in generative art and computational creativity. Creative tasks do not have optimality criteria or well-defined goal states as a direct consequence of their definitions. Therefore, it makes intuitive sense for the authors of creative systems to use domain-specific heuristics, and in the case of art, their specific knowledge and bias to guide the search, that is, the generation. The term heuristic can be used in at least two senses. A heuristic can be an aid to learning and discovery that is validated mostly by trial and error. In other words, it is a rule of thumb. More formally, heuristics can also refer to methods used to limit the size of the search space. Note that these two definitions are not mutually exclusive. Most heuristics are domain-specific tricks, while there are also some generic heuristics. Also note that this is linked to our initial distinctions between specific and generic systems. The more a system relies on domain-dependent knowledge and specific heuristics, the less generic it will be. This will impact the stylistic signature of the system. The heuristics can come from the author or be learned by induction from existing data and constitute the knowledge of the system. One of the earliest examples of musical agent was an accompaniment interpretation system by Roger Dannenberg from 1984. Here, the system does not generate the accompaniment to the melody because the complete score is known. Instead, the challenge is to follow along and interpret the accompaniment in the best possible way, given an unsteady tempo and the possibility of the soloist adding or removing notes by mistake. The system uses a collection of heuristics to determine where in the score the soloist is and what to do next. Of course, any input into the system can be seen as information that can be used to guide and restrict the search, that is, the system behavior. A travel guide is a 2014 geolocated web art piece by Alison Parrish. It consists of a web interface through which one can access to a travel guide based on the place you are. The travel guide is generated on the spot by a recombination of sentences from Wikitravel. Whatever the search strategy is, one searches for something. The fundamental problem of computational creativity is defining what we are searching for. What is a goal state and what is a good quality solution to a creative task? This is a difficult problem. As we already discovered in this class, it is not easy to measure success at creativity. We have several families of solutions to this problem. We saw that many attempts have been made to devise aesthetic functions to complement the functional criteria of the tasks, if it has any, but solutions using formalized analytical criteria and ratios are imperfect, often insufficient, and sometimes controversial. A second family of approaches is to let a human judge the quality of the solution, like with interactive evolution or interactive search systems. We saw how this proposes a radical change to the design process and opens many possibilities, but we also saw how this often introduces a bottleneck in the search. We saw how difficult it is to learn aesthetic preferences from human subjects. The third family of approaches are data-driven methods, using examples of artifacts that were novel and valuable. A similarity measure is then used to determine how a given artifact fares against an exemplar or a set of exemplars. The problem with data-driven approaches is that if the system ever converges and the search succeeds, it will converge to artifacts we already have, those exemplars or good approximation of these. That does not constitute something truly novel and valuable. It is hard to define the goal of the search, but maybe this goal-driven, objective-driven type of search is just not the right one. Kenneth Stanley, a researcher in evolutionary computing, is of the opinion that guiding the search using this metric of optimization is the wrong way to try to achieve creative outcomes. After 6 years of operation, the users of PicBreeder, the crowdsourcing picture breeding online platform that we studied together, had collectively evolved over 9,000 images. Some of them are quite exceptional when you consider that these are encoded as a network of simple mathematical functions and transformations. In an attempt to automatically grow interesting images, Stanley's team used pictures evolved in PicBreeder by humans as a target function for an automatic evolutionary search. In other words, they used the neuroevolution approach NEAT to try to replicate pictures bred by humans with PicBreeder. Interestingly, the system was not capable of evolving the NEAT networks corresponding to those pictures. After 33,000 generations, the best results were still very far from the target. Stanley and his team were surprised and went back to observe the phylogenetic trees of the images generated by humans. They realized that often, some intermediary images or stepping stones images along the way during the evolution were very far from the target image. The fact that these were not clearly on the road from the blank canvas to the target explained why NEAT would get stuck into local optima and fail to converge back to those images. The idea of novel search is to use a different approach to navigate the search space without a precise objective or target. Our goal in general is to find novel and valuable points in the search space, right? Since quantifying what is valuable, interesting, and aesthetically pleasing is difficult, let's focus on novelty. Novelty does not necessarily mean that we know where we are going, so we do not need to care about how far we are from the given target. Instead, we use where we have been to judge when and how much novelty we have and how far we can get from where we've been. With novelty search, the fitness of an individual is judged by his distance from the other individuals produced before. The assumption is that in general, the greater the distance, the more novel a given individual will be. What is stupefying is that we can also solve objective rational problems through novelty search, and sometimes this works better than goal-oriented search. Here, Stanley used the NEAT framework to evolve neural networks using novelty as a fitness function. To use novelty as a fitness function, instead of trying to get closer to the target, we try to maximize the distance from where we have been before. Let's take the example of evolving agents' brains or controllers in a maze crossing tasks. It could be any maze, but let's consider this maze, in which the small dot at the top is the goal, and the white dot at the bottom is the initial position of the robot. We see that it is a somewhat complex maze because there is no direct path and there is a cul-de-sac here that acts as a potential local optimum for the agents to get stuck in. Stanley and his team ran 3 different conditions. One condition used the distance to the goal as a fitness function, which is a typical objective function for this type of search. One used a random fitness function, and one used novelty search by rewarding the robots that went further from where the others have been before. Out of 40 evolutionary runs, only 3 were successful running the objective fitness function, 4 with the random fitness, and 39 out of 40 with novelty search. While it makes sense that the objective fitness did not do well and that most of those robots would get stuck in this cul-de-sac, it is initially puzzling that novelty search would do so well and so much better than a random fitness or objective function-based search. On further thought, it makes sense because novelty search makes the robot explore more of the maze in order to find places that have new coordinates further from already visited places. Novelty search allows the robot to get over the local minima of the cul-de-sac. Similar successes have been achieved for other problems too. For example, when evolving a network to control a biped robot and evolve walking, it was found that the gait evolved through novelty search performed better than a fitness function based on speed or distance traveled. The novelty search function rewarded a gait that got the robot somewhere none of the other robots had been to. It turns out that the stepping stones toward better walking are not the ones we would think of. Of course, the technique is limited, and the trade-off is that we give up on searching for something specific. The Innovation Engine is a 2015 piece that builds on novelty search as a search technique. However, it replaces the human-crafted behavioral distance function with a deep neural network. This network recognizes interesting differences between phenotypes by measuring how compressible they are in ways inspired by Young and Schmidt-Huber approach to creativity that we will study later on in this class. This research function pressures the system to produce different types of images. The first version of the system evolved expression-based images. The deep neural network is an object classifier with 4,000 categories, and generated images were selected and kept only when they fell into a high confidence zone for one of those categories. Here, we see images grown by the network alongside the Google Images search results for searching on the same keyword. We can see the similarity in the features of the images generated and the images retrieved. The Achilles heel of stochastic optimization algorithm is getting trapped in local optima. Novelty search provides a way to work around this problem because it encourages the search to go in all possible directions. To implement novelty search, we reward novel behavior instead of rewarding progress toward the goal. Novelty is typically measured with a manually defined behavioral distance function. Novelty search is more than just a twisted fitness function. In the case of novelty search, the fitness of an individual depends on the other individual generated or encountered so far, which is not the case for a regular fitness function. It could also be called diversity search or curiosity-driven exploration. Search is a vast topic in computer science. In their groundbreaking work from the 60s, artificial intelligence pioneers established that every rational problem can be mapped to a search. In this lesson, we saw how the search paradigm can be used to formalize exploratory creativity. Most generative methods we studied so far can be reformulated as a search. The search can happen at several levels of abstraction. The search can be about the artifacts themselves, or it can be about their representation. In that case, we search a set of possible search spaces, each corresponding to a given representation for the individuals. Or the search can be about the search technique itself, in which case we search a set of possible search techniques, or we search the heuristics or the other guides to the search itself. In machine learning, this idea of searching the set of search spaces is known as searching the bias space. In artificial intelligence, it is called meta-search, or search at the meta level. Be it Bruce Buchanan in his 2000 AAAI presidential address titled Creativity at the Meta Level, or the creative system framework formalism to describe creativity as such by computational creativity researcher Geraint Wiggins, the notion of such at the meta level has been discussed as being a way to open avenues to formalize transformational creativity. In this lesson, we surveyed a variety of such-based approaches to generative art and computational creativity. And with novelty search, we saw how new ways to look at such algorithm can emerge from it.